Sharif, please go ahead.
Okay, sir. Okay. Sir, I'm audible?
Yes, please go ahead.
Okay. So, warm welcome to all the participants to day third of our 7 days international workshop on frontier in structural equation modeling. So, it is organized by Jammu and Kashmir Economic Associations, Global South Research Foundations, in the collaborations with the Crescent Institute of Science and Technology, Creek University Bangkok, Deep Skills in and Social Sciences and Humanity International. So, today we move an important aspects of the structural modeling and path analysis, where we will focus on the evaluating the structural relationship, path coefficients, and hypothesis testing and model fit. So we have today our experts, Dr. Chanda Gulati. She is professor of HRM and head of IQACS Prestige Institute of Management and Research, Gwalior. So she has 14 years of academic and 2.5 years of the corporate experience, and she holds a PhD from Jivaji University and MBA from VIT University. She has published widely in ABDC, Scopus, and Web of Science journals. She has edited 9 books, contributed to e-Pathshala book initiatives, and earned the multiple Best Paper awards. She also served the review board of the reputed journals. Her expertise spans on internal branding, HR practices, and organizational behavior. So we look forward to an insightful sessions under her guidance. So let us begin for today's sessions. So ma'am, over to you.
Thank you, Dr. Sharif. Thank you, Dr. Firdaus, for such a warm welcome. So, I think the topic is very vast. So, without wasting any time, we should start delving into the topic, right? So, let me share the slides. It's visible?
Yes, yes, ma'am, it's visible.
Is it in the slide presentation mode now?
Yes, ma'am.
Huh?
Yes,
It's changing also?
yes, yes,
I'm able to change it, right?
yes, yes, ma'am. Yes,
Fine,
it's okay.
fine, fine. Thank you. So let's start with the structural models assessment. I think in day one and day two, you must have been exposed to the outer model, inner model, and the prerequisites of PLS SEM, right? So let's start with that, what this structural model actually deals with, what are the prerequisites once again, and then we will go into the practical hands-on experience, right? So the structural model assessment is basically to analyze the structural relationship between latent constructs. Now, basically the structural model assessment, if we say PLS SEM is basically based on variance-based SEM. That means it is only required when your aim is prediction and explaining the variance, not about testing the theory and its confirmation. If we are talking about testing the theory and confirming the same, then preferably we will go for MOS. But if we are opting for PLS SEM, that means we are into the variance-based SEM, right? And the main focus is what? That means when we should use PLS SEM. PLS SEM is basically being used when your prediction orientation is clear. That means the goal should be to maximize the R square. The goal is what? To maximize the R square and understand that which of the independent variables or is contributing best in predicting the endogenous variable. That means the dependent variable. That means it should be prediction oriented. what is this second point? Handles complex model. See, if we go for a simple linear regression model, we can check uh, relationship between one construct on another construct. But here, if for suppose I'm saying PLS-SEM, that means I can put on lot many mediating variable, lot many moderating variable at a time. That's how I can make it very complex. And then also PLS-SEM is powerful enough to compute the prediction, right? The third advantage is it even works with the smaller samples. That means even if you are having 100 or fewer observations, it is more than sufficient. You can go ahead with PLS-SEM, right? No strict distribution assumption is required. That means your data is normal, not normal, is not a mandate requirement for running PLS-SEM. It is suitable for both formative and reflective constructs. That means because nowadays in the real world, we are having more of the formative constructs. For example, I will take service quality. Service quality is a formative construct which are being measured or which is being formed through its dimensions. If any of the dimensions we will remove, probably the meaning of the service quality will change, right? So that's how PLS-SEM caters to all these points. One, prediction oriented. It can handle the complex model. It will work very well with the small samples. No normality of the data is being required. And formative, reflective construct, whatever type of constructs you have, you can put in the model and you can run the PLS-SEM, right? Now comes when or how PLS-SEM basically works. PLS-SEM has two models. One is the outer model and the other one is the inner model. PLS-SEM very first outer model is also been known as the measurement model. Here in measurement model, what we try to understand, we try to examine how survey instruments, that means the survey items that you have used to collect the data, that represents a construct. That means I'm talking about the reflective constructs and the formative constructs. As, as just shown over here, this is the reflective construct. That means the indicators, CS1, CS2, CS3, CS4, CS5, it is reflecting the customer satisfaction, right? The question items are reflecting the customer satisfaction, right? If it is a reflective construct, that means dropping any one of the indicator does not change the meaning of the customer satisfaction, right? And if, for suppose, I'm saying that the satisfaction is increasing, that means all the items score might move or might move up. That means might increase. Then comes formative constructs. Formative constructs means the indicators are forming the constructs. Tangibility, reliability, assurance, responsiveness. These all are helping in forming this service quality construct. Because of these only, this service quality exists. If for suppose I remove reliability from here, whether I'm able to justify the meaning of quality, no, one of the quality criteria is missing, right? So that's how in, if I'm saying it is formative, that means I have to take care of all the dimensions. We cannot miss on any of the dimensions. You can take another example of formative construct also, that is socioeconomic factors. Which all are the socioeconomic factors? Income is one of the factor. Education is one of the factor. By removing income, can I say that I'm measuring the socioeconomic factors completely? No. If I'm removing education, can I say that I'm justifying that term socioeconomic factors? No, right? That means all the indicators are required to form that construct. So this is what is the measurement model. If I'm saying how PLS-SEM works, so first what we have to do, first we have to assess the measurement model, confirming the quality criteria of these constructs and how this quality criteria can be established by knowing the reliability and the validity that you must have learned yesterday, right? That what are the reliability measures, what are the validity measures. If it is coming in the acceptable range, then only you can move for the structural modeling establishment, right? So next is, for suppose the rule of thumb, as I stated, that the measurement model estimate must be acceptable. If it is not acceptable, you cannot move ahead to measure the structural model. So what does this structural model does? Structural model is also known as the inner model of your model, the complete SEM model, that tests the relationship between the constructs, right? That is, for example, service quality, relationship of service quality and customer satisfaction, relationship of customer satisfaction and customer loyalty, relationship of service quality on customer loyalty, right? This construct relationship is being established by structural model. So let's start with structural model assessment. So what is this construct? These constructs are the theoretical constructs, also known as the latent variable. For example, motivation, satisfaction, service quality, performance, engagement, right? And in the structural model, we try to hypothesize how one construct influences another construct, right? For example, I have taken H1. Hypothesis 1 indicates what? Motivation uh, is influencing job satisfaction, or motivation has an effect on job satisfaction. The arrow, the directional arrow basically represents what? The causal or the predictive relationship between the latent variables. This is what is the theoretical model that you have made out of your reviews. These are the 5-step procedure of structural model assessment. Step 1 is the assessment of structural model for collinearity. That means these are few things that we need to check. The first thing that we check is structural model collinearity. The second thing is assessing the significance and relevance of structural model relationship. That means the path coefficient, t value, and p value. Then the third step is assessing the explanatory power of R square, right? That how much variance is explained by the exogenous variable on the endogenous variable. And the fourth step is assessing the effect size of all the predictors that we call F squared, right? And the last step is assessing the predictive relevance. That means out of sample prediction power of your model that we compute through PLS predict and CVPAT. So let's start with see, Ringel et al. In 2018 has published one of the book, one of a paper in European Business Review named "When to Use and How to Report the Results of PLS SEM." In that he has also given the aspects and statistics to be considered in a PLS SEM analysis. VIF, that means we are talking about the collinearity, explanatory power, R square, out of sample predictive. That means prediction power is PLS predict, Q square, and R CVPAT. Significance and relevance of the path coefficient and model comparison is CVPAT. So moving ahead to step by step in Smart PLS, that how we will be constructing it. So first we will be selecting any of the data set. We'll build a model. We'll run the PLS algorithm. We'll run bootstrapping. We'll try to interpret the hypothesis and we'll assess the quality of your model. That means through R square, F square, or the predictive Q square. So let me share Smart PLS. Is it visible? Is
Yes,
Smart,
ma'am.
Yes, ma'am,
Smart
it's
PLS
visible.
4 is visible? Fine, fine. So
Yes.
let's create a new project here. See, data set that you are going to use here must be saved in CSV file, right? Let's name the project workshop SEM. Now import the data file. Let's take one of the SEM data file.
Madam, we are unable to see it. So PPT.
No,
Ma'am, you
no,
are
I'm not showing the PPT. I'm showing the sheet. It's not
ma'am,
visible.
ma'am, your sheet is not visible. Your PPT is visible.
PPT is visible. 1 second, sir. One second, then I will start from the scratch.
If you share entire screen, maybe then it will be visible.
One second, let me stop the share. Is it visible now?
Yes, ma'am. Now it's visible.
Now it is visible. Now PPT is
Yes.
also visible in parallel,
Yes, ma'am.
right?
Yes, ma'am.
Fine,
Both are
fine.
visible.
Thank you.
Now
Thank
it's
you
fine.
so much.
Okay.
See, what I have done so far, let me delete this part. Let me start fresh. Right. Let me mention workshop SEM, right? Create it. Let's import the data. Go back, create a model, choose a model type as we are doing PLS SEM. Let's name it SCM only. Save it. Now I'm having this interface. What I will be doing, I'll be taking my independent variable, right? I'll take all the independent variable on board here. Independent variable 1, independent variable 2, independent variable 3, right? I'm not taking in any mediating variable at present. Take the dependent variable. Hmm. Yes. Let's do some adjustment. Okay. This is the dependent variable. Now let's connect. You can also rename these variable. For the session, I have kept it independent variable only. You can rename it. For suppose it is motivation, satisfaction, HR policies, and all are affecting your performance, right? You can rename it. Now let's go back to the PPT. See, the very first step was what? The first step was this. Is visible, right? So the very first step
Yes,
was
ma'am.
assessing the multicollinearity, right? This is what we have to do now. Now, if I'm saying collinearity, what do you understand? Anyone? If I say it is collinearity, what do you understand from that? No?
Collinearity is basically the correlation between the items of different construct
Fine.
or
Very good.
maybe of the same construct.
Exactly. Collinearity is basically the correlation between the items of the same construct or between the constructs. Both are possible, right? So this collinearity is basically being measured through this VIF value. So VIF tells you whether two or more independent variables in your model are fighting with each other because they carry the same kind of information, right? That means if they are carrying the same kind of information, this confusion itself is known as multicollinearity. That means that confusion has to be dropped, has to be minimized. Clear? So VIF will be explaining the collinearity statistics. Now there, here et al. Has actually given some standard value of VIF. If, for suppose your VIF value is 1, then it is perfect. That means it is lesser than 3.3. There are all the items you can assume that they are giving the unique information. If it is indicating in the output of PLS SEM 3.325, that means up to 5, that means it is a matter of concern. There may be small overlaps. And if it is red, that means the VIF value must be more than 5. That means it is a warning zone. You must look for the similarity in the variable. If more than 10 is a very serious problem, so try doing anything to mitigate this issue. So how to address the multicollinearity, that also we'll see. In that, what we can do to do that, that means to address this multicollinearity, we can remove the variable or the item. We can combine the variables also to form a new combined construct. We can, if for suppose I don't want to remove any item or the variable, or we don't even want to combine the variables, what I can do? I can go to increase the sample size. That's the another way, right? So let's see in the model that how it works. Go to the calculate part, go to PLS SEM algorithm, path analysis, and run this model. Now, let's check for collinearity statistics. One second. See the collinearity statistics. Dependent variable 2 showing highest VIF 11.603. It is as stated, it is the major concern. You need to remove that. Dependent variable 3 is also showing 10.483. That is also a major concern. Instead of removing all at a time, let's remove one by one to check whether it is affecting or your multicollinearity issue is getting settled down. It was DV2, I think, was showing the highest. So let's remove this. One second. One second. It got hanged. Fine. This I have deleted. Now again try to run this PLS SEM. Check for the output. Go to the quality criteria. Click on collinearity statistics. See, further improved. That means now we are below 10, not that severe. So that's how one by one we can try improving this. We are not suggesting that you remove all the items. Probably that construct will itself will get removed. So what we can do, if it is a severe issue, then you can try removing that item so that the VIF value will be considerable for this for running the model, right? So now let's move to the second step. What was the step 2? Step 2 was about assessing the significance and relevance of structural model relationship. That means we are talking about the path coefficient. Path coefficient is basically what? Path coefficient is the measure of strength and direction of the influence between the two constructs. That means it's actually talking about the beta value. Path coefficient is explaining the degree of change in the endogenous variable for every 1 unit change in the exogenous variable. Predictor variable में जो भी change होगा, that should be reflected on your endogenous, that means the dependent variable. So standard beta value lies between +1 to -1. For suppose beta value over 0.10 means it's having a significant relationship. We cannot say significant relationship yet until unless you run bootstrapping and you confirm that statistics and p value both are coherent, both are supporting your hypothesis, right? So let's try checking this also. Go to bootstrap. Now, once we go to the bootstrap, what is this bootstrap? As in the starting, I stated that even the non-normal data can be tested on PLS-SEM. So bootstrap is a non-parametric distribution-free test. It's a resampling technique used in PLS-SEM to test the significance of the paths and the loadings and all, right? Instead of assuming the normality, the software does what? The software repeatedly draws subsamples from your original data set. And for how many times it is doing? It is doing for 5,000 times, right? So PLS-SEM is doing what? In bootstrapping, they're trying to draw the subsample from the original data set and builds a distribution of estimates, thus making it normal, right? So each subsample is used to re-estimate the model, then automatically the normality issue is mitigated, right? Then comes here, you can say that we are even taking percentile bootstrap. What is this percentile bootstrap? Smart PLS first takes what? Takes 5,000 bootstrapping estimate. Then in percentile bootstrap, they try that 2.5th percentile and 97.5th percentile. What is 2.5th percentile? If you know confidence interval, we usually take it 95%. Huh? We used to keep it 95%. So 95%, that means 5%. We divided that 5% into 2.5% at the lower end and 2.5% at the higher end. 2.5%, that means 2.5th percentile, and 2.5% at the higher end, that means 97.5th percentile. What is 2.5% of 5,000? 2.5% of 5,000 is 125th value, right? 120. That means bootstrapping has run this model 5,000 times, right? What beta value I have taken, which has come at the 125th position. The value that has not come on the first run, but the value that has come on running this model at 125th time, right? And similarly, 97.5 percentile. That means 97.5% of 5,000 means what? 4,875. This is the position. When we run this model for 5,000 times, whatever beta value has come, when we were running it at 4,875, that value is being considered, right? So that's how a confidence interval method is being used. But the only thing that we assume that 95% of the results fall between these 2 points. That is what is the interval. And the only key idea is 0 should not fall inside it. If 0 is not inside the interval, that means your effect is significant. If 0 is inside, your effect is non-significant, even if you are getting good beta value, right? Now, coming to the third type, when to consider two-tail test and when to consider one-tail test. Tail is what? Tail is actually the direction. If you're saying two-tail test, that means I don't know the direction. Fine? I don't know the direction. That means whether the motivation is having a positive effect on job satisfaction or motivation is having a negative effect. That means motivation increases satisfaction or motivation decreases satisfaction, that I don't know. If you don't know the direction, you can consider two-tailed test. If you know the direction, that means your review is suggesting that no, it will always have a positive effect. Then you can go for one-tailed test. So for the safer side, what we do, we take two-tailed test, right? Then comes the significance level. The significance level is always being considered at 5%. That means 0.05. If your significance level, significance value, that is the p value, is probability value, is lesser than 0.05, the significance is established. Your model is significant. If it is more than 0.05, that means it is insignificant at 5% of interval. If we say 1%, then 0.01. More than 0.01, it is insignificant. Lesser than 0.01, it is significant. But in majority of the case, we consider the significance level cutoff as 0.05, right? Then the last one is fixed seed. Now, what is this fixed seed? Fixed seed, we can say that here the seed is starting point. Seed is basically the starting point. Why this is needed? Why we are not saying it is a random seed? Why we are going for the fixed seed? Because bootstrapping uses randomness to draw the samples. Bootstrapping is already saying that randomly they are resampling. They are creating the subsamples, right? Why we fix a seed? Because of the randomness nature of the bootstrapping, it is advisable to avoid small random variations in the computation. We try to fix a seed number. For suppose, we will start the calculation from 11111. That means start with the seed number 11111 so that the variations can be mitigated. Variations ज़्यादा ना हो, इसके लिए we try to fix this seed. If seed is fixed, both get the identical result. That means I have fixed the seed, and in the first run also, and in the second run also, probably there will not be that much variation in the result that we'll be getting by running PLS SEM. Fine. Now, let's start this calculation. We were computing path coefficient. Let's check with this path coefficient. See, independent variable 1 is having the beta value between independent variable 1 and dependent variable is 0.230, and this is significant, right? So that's how we can say that independent variable 1 is having an effect on dependent variable, and this beta value is value is positive also. So we can say that independent variable 1 has a positive effect on dependent variable. Independent variable 2 similarly had a positive effect on dependent variable. Here, p value is not significant. That means it is more than 0.05, right? So even if the beta value is reflected here, path coefficient is 0.056, but it is insignificant. Independent variable 3 is not having effect on dependent variable, right? Let's move back to the slides. This is how we mention this, how we report this relationship. For suppose hypothesis 1 was motivation is affecting training and beta value that you received is 0.45, right? T value we will also talk about the T value. T value in two-tailed test. T value that is being considered is it should be more than 1.96. for 5% level of significance. So is t value, you can check in the model that I have tested. I will just show that also, that how it is being computed. Then if I look at the hypothesis 2, training, whether training is having an effect on productivity, here also I can see that beta value is 0.55, t value is this, and p value is lesser than 0.05. That's how this hypothesis is also supported. But if I look at hypothesis 3, wherein the motivation effect on productivity has been checked, beta value is 0.12, t is 1.45, right? T is also not up to the mark. That means it should be more than 1.96. P value is also not significant. That's how this hypothesis has not been supported. So while reporting your relationship in a paper, while you are writing the research paper, you can report it in a tabular form, then you can narrate and support it with the review that you have collected. Now moving ahead to the step 3, assessing the explanatory power. We must have heard about the R square, right? R square के बारे में सुना होगा आप लोगों ने. So what does this R square actually indicates? R square is like a report card score. It is explaining the variance explained in the endogenous variable. That means, of course, as you see in the model, I have taken 3 predictor variable, and 1 dependent variable. That means 3 exogenous variable and 1 endogenous variable. So what the R square is actually explaining, that how much variance has been explained by exogenous variable 1 on endogenous variable, how much has been explained by in exogenous variable 2 on endogenous variable. Together we are actually computing R square adjusted, right? But this is in sample predictive power. That means as per our data set, we are calculating the explanatory power of our model. The explanatory power of our model is reflected by R square. Value, if the value of the R square is closer to 1, that means it's having a high explanatory power. Here et al. Has also supported that R square value lesser than 0.25, we consider it weak. R square value up to 0.50, it's moderate. R square value more than 0.75 is strong. For example, if it has been written, R square value is of 0.268, and there are 2 independent variable and 1 dependent variable. How you can narrate it? That 26.8% change in Y is explained by these 2 variable. Remaining are not yet been explained. That means there might be few more exogenous variable that are explaining those remaining uh, variance, right? Only 26.8% have been explained by X1, X2. Probably there are X3, X4, X5 that are explaining the remaining variance, right? Now, let's see that from where you check this R square. This is R square, 0.282, right? This one is the R square. 28.2% of variance is explained by independent variable 1, 2, and 3. Fine. Now coming to the next step, step 4. Now estimating the effect size, that is F square. Effect size of the predictor. What is this effect size? As seen in the model, I have considered 3 of the variable. Variable 1, variable 2, independent variable 1, 2, and 3. These 3 exogenous variable is predicting 1 endogenous variable, right? Effect size of the predictor means how much contribution or is there of independent variable 1 on dependent variable, independent variable 2 on dependent variable, and independent variable 3 on dependent variable. That means change in R square is being measured so that you can understand the effect size, that which one is more powerful predictor of endogenous variable, right? The Cohen 1988 has given few of the benchmarks. If it is R squared change is 0.02. That means there is a smaller effect. If R squared change is up to 0.15, it is medium effect. If it is more than 0.35, that means it's having a larger effect. Now let's check this in the model. At present, we are having, what is this? R square. Let's add, let's keep it like this only. It is 0.282, this R square. Fine. Now what I'm trying to do, let's remove independent variable 2. Fine. I've removed independent variable 2. Now start computing again. What's the R square value now? It is 0.057. What's the difference? 0.225. Fine. What Cohen has explained, Cohen 1988, he said, if it is more than 0.15, it is medium. That means independent variable power of predicting endogenous variable is above medium, right? It's not large, but it is having a good effect size. Now, let's go back to this model. Remove this independent variable 1. Let's compute again. Remember the initial R square, it was 0.282. Again, I'm running the bootstrap. It was 0.282. Now the R square has dropped down to 0.229. What's the change? What is the change? 0.053, right? 0.053. What Cohen has said about this? If it is 0.053, it is smaller. It's having smaller. That means independent variable 2 was a better predictor of the endogenous variable. So that's how we check the effect size. That which of the exogenous variable is better predictor of your model, right? This is how we can check, right? So R square is stating what? Explained by the model, and unexplained, that means there are remaining few variables, are exogenous variables are still there, which can predict your complete endogenous variable well. That means something is missing in your model. And if I check about the F square, that means compare how strongly each predictor contributes to the outcome. As in this case, we have seen that predictor B, independent variable 2, was a better predictor than independent variable 1, right? Now moving ahead to assessing predictive relevance. Till here, is there any question?
Ma'am, can you please repeat how to read effect size in the model? I missed
One
that
second.
part.
One second. See, I'm running it again. This was my original model, right? This was my original model. Here, what I do, I'll try to run bootstrapping. This is R square, right? R square is what? The variance explained by the exogenous variable. These are the exogenous variable on endogenous variable. That means these variables, these independent variable are explaining 28.2% of variance in independent variable, right? So just mention it. It is 0.282. 0.282. Now what I did, first I tried removing, go to the edit option. First, I tried removing independent variable 1. Again, I ran the bootstrap. This R square value has dropped down to 0.229, right? This dropped down to 0.229 to initial R square, right? This value from the initial R square, that was 0.282 minus 0.229. That means what is the value that you are getting? 0.053. Right? What Cohen has actually stated? Cohen has stated that means, that is, if it is this change in R square is 0.02 or more than that, that means 0.02, in between 0.02 and 0.15, that means there is a smaller effect. That means it is predicting, no doubt, exogenous variable 1 is predicting your dependent variable, but is having a smaller effect, not that powerful predictor, right? Now I'm going back and I'm trying to remove some another variable. In this case, I removed second variable. I tried running bootstrap again. Was a drop? We were standing on the value initially that we received was 0.282. It has dropped down to 0.057. What's the difference? 0.225. I think change in R square is higher. Now, if the change in R square is higher, it is 0.225. That means it is lying between medium and large. See, change in R square is between 0.15. The value that I am receiving is 0.225 change in R square. That means 0.282 minus 0.057. Fine. So that's how I can say that independent variable 2 is a better predictor of dependent variable instead of independent variable 1. Why I have not tested on independent variable 3? Because it was already insignificant. Right? I think you understood?
Yes, ma'am. I've got the things which I have missed out. Thank you so much.
Okay, most welcome. Now let's move ahead. Let's move to PLS predict, right? So far, what we were actually trying to predict was in-sample prediction. Now, what is in-sample prediction and what is out-sample prediction, that we will talk about, and then we'll move ahead. See, in-sample prediction, that means we are trying to test our existing data set that we have collected through survey. Out-sample prediction means what? I'm actually trying to test the predictive power of your model for a new data set, right? We'll see how it actually been done. PLS predict, if you see, for example, imagine you want to predict a student's productivity, right? If you want to predict students' productivity based on motivation and training, you build a PLS model. PLS model आपने बनाया. You took motivation as one of the variable and training as another variable. Both are trying to predict the productivity of the student. But now comes out of sample test. In sample mein to I'm running the PLS SEM and I will get a result. I can say that whether motivation has an effect on productivity or not, or training has an effect on productivity or not. But if I take a new student, can my model predict their productivity? So that new student data set is for the new observation that is not available in your model, right? So predictive, that means we are not confining our SEM modeling only to predict your explanatory power. We are moving ahead to understand whether your model can even predict the new data, right? And that is being predicted, assessed through Q square. Q square talks about your predictive relevance of the model. Hare et al. In 2013 has said that if the Q square is more than 0.02 value, it is weak. Your model is having a weak prediction relevance. If it is more than 0.15, then it is moderate. If it is more than 0.35, that means it's having a very strong predictive relevance, right? Who had actually proposed this PLS predict? Shimley et al. In 2016 has talked about PLS predict procedure for out of sample prediction, right? So in PLS predict, what we will be doing, we will be dividing the sample in two. That means training sample and holdout sample. How we do that? Just check. Take the full data set. For example, take the full data set. Think of this full class of student, for example, right? That you have marks of 100 students in maths. Now, what we will be doing, this holdout sample is what? We are trying to remove a small portion, for suppose 20% of the sample, and hide their marks, right? Now, why we are actually doing this? We are trying to test whether your model can predict marks it has never seen, right? Now, what I will be doing, I'll be building my model for remaining 80 student. That means training sample. This training. This we call k-fold cross validation. If we go in the smart PLS to make it very simpler, the k-fold is anonymously has been mentioned over there that what should be the k-fold, right? For that, we need not move here and there. Let's go to this PLS. Go to calculate, go to PLS predict. The k-fold is what? 10. Start the calculation. PLS predict latent variable. What we stated, that if your PLS Q square predict value is more than 0, here it is 0.257. That means is having a predictive relevance to that. That means your model can work in the real world, not just on your own data set. It means whatever model you have made and you have tested is not only applicable on the present data set, even if you are modeling it on a new data set, probably it will be giving the same kind of relationship, right? That means it will be, even if you work on the different data sets many multiple times, it is having a predictive relevance and is having a strong predictive power, right? This is what has been written. If predicted values are close to the real values, model has a good predictive power. If predictive value is far off, that means the model is having is not a good predictive power. That means probably the same relationship cannot be established with a new data set. Similarly, in this prediction, we are having one more uh, inclusion at present that we call CVPAT. CVPAT is the cross-validated predictive ability test. It stands for cross-validated predictive ability test. It is a prediction competition between two models. Now, what's the difference between PLS predict and CVPAT? PLS predict tests the prediction accuracy. Can your model predict new data set well? Right? CVPAT is model comparison. That means compares predictions of two models. Which model predicts it better? Right? So CVPAT checks which model predict the endogenous variable better. Your PLS SEM model or the benchmark model that is there available. That means I'm running a linear model, a simple regression. That is a better predictor, or your PLS SEM model constituting of complex is comprising of several predicting variable is predicting the endogenous variable better, right? For example, I will say, for suppose a teacher uses method 1 to compute marks of the student. It is PLS SEM. And in second case, teacher B uses method 2 to compute the marks of the student. That is the benchmark. Now assign them a new set of students. Who is able to predict the marks of the new set of students more accurately? If teacher A makes fewer mistakes, PLS SEM will win. If teacher B makes fewer mistake here, then that means the benchmark, that means the linear model or the IA, average indicators, right? Indicators average, they can win, right? So CVPAT is basically this comparison between the two models. CVPAT compares three ways. One is IA, that is the indicator average. Indicator average uses a simple averages. That means average of three items, right? Linear model is a regression equation, and PLS SEM is basically not many paths that you have created in your model. That means one construct is having effect on the another is having the effect on another, and that's how the performance you are going to measure, right? Here, directly you are measuring the performance through its items. That you are doing an average here, and here you are actually constituting a linear regression. That means effect of X on Y, right? Here I'm taking up lot many constructs to measure the effect on job performance. Now let's see that how PLS is this CVPAT will be taken care of. Go to calculate. The model is same. Go to PLS predict CVPAT. Run the model. Come directly. There is a CVPAT latent variable summary. Come to this. If this PLS loss is negative, basically we consider if this PLS, that means if in this case, actually we are having PLS loss positive, right? And this one, no, sorry, PLS loss and this one is IA loss, that means indicator average loss. The once you compute the difference between the two, you are getting the average loss in negative. If it is negative, T value more than 1.96 and P significant, that means your model is a better predictor than a normal linear regression, linear model, or the average, this indicator average model. That means this average loss should always be negative. Clear? And it should be significant also. This is how we report this CVPAT in paper. You will state that in both PLS SEM and indicator averages or PLS SEM and linear model, we obtain a negative average loss that is reflected here in this column, negative average loss, which means PLS-SEM has lower average loss in comparison to. That means the error we have done is lesser, right? PLS-SEM has lower average loss in comparison to IA and LM. That means indicator average and linear model benchmarks. And the value is significant. That is, p-value is lesser than 0.05. Thus how PLS-SEM model that you have chosen has better predictive capabilities, right? So that's how CVPAT, just remember that CVPAT helps you in compare the model with the benchmark. That means your PLS model that you have constituted and a simple linear model or indicator average model, right? And PLS predict is actually helping you in calculating that whether your model that you have prepared is is having the capability or capacity to predict the new data as well, right? So this is what is the difference between the two. A slighter difference, but yes, it do exist. See, this is what has been mentioned. Average loss difference, that means PLS error minus benchmark error. If PLS makes smaller error, you get PLS error minus benchmark error. That means if it is lesser than 0, it is negative. That means your PLS model is a better predictor than the benchmark error. That means what's the benchmark here? The linear regression model or indicator average model. See, in nutshell, these are the metrics that we usually uh, report while writing the results in paper. Path coefficient you need to take care of, that whether it is falling on the acceptable range or not, closer to plus and minus 1. That if it is between this, that means it is stronger. Plus and minus, that means it's actually giving stating the uh, uh, direction of your relationship, whether it is positive or negative. T value, it is talking about the statistical significance. It should, if it is a two-tailed test, it should be more than 1.96 as well as significant. P value, that means the probability value should always be lesser than 0.05, then only it will be considered significant. R square, that means the percent variance explained in dependent constructs. If it is 0.25, we assume it weak, but in social science that also works, right? If it is 0.50, it is moderate, and if it is 0.75, we assume that exogenous variable is a very powerful explaining variable uh, in explaining variance in dependent variable. F square, that is the effect size of the predictor. If 0.02, we consider it is small. If 0.15, it is medium or moderate. If more than 0.35, that means it's having a larger effect. And Q square, that is PLS predict or CVPAT. If Q square is more than 0 or CVPAT, the average loss is negative. That means your model is having better predictive relevance, right? That's all from my side. If you are having any queries, you may go ahead.
And dear participants, if you have any query, any questions from these sessions, so we are ready for taking any questions.
Madam,
Yes.
in some models, if there are two dependent variable, madam,
Mm-hmm.
so how this I mean like coefficient and path coefficient, this all will be done, madam.
See, as stated in the beginning itself, that your PLS ACM is a very powerful tool. As many as mediating, moderating, or dependent variable you want to introduce, you can introduce. For suppose, let's take this variable as the another dependent variable. Fine. Try to connect. It will work in the same way. Go to calculate, go to PLS session. See, the path coefficients are visible.
Yes, ma'am. Yes.
Fine. So it will never be an issue. You can, for suppose I don't want to make it dependent itself. Although these three variables are predicting it much more better. The R square is 0.304. But you can even make it in that way that, yes, one second. I think I stopped. This was the model. Try to connect. Fine. Now again I'm running. I think in the next session you'll be learning mediation. Now try to run again. See how dependent variable R square has increased. That means this variable is acting as a mediating variable in between these two. That's how it is the explanatory power of these variables together along with this mediating variable has boosted the R square value. Got it? You can even check further by bootstrapping. You can check the significance of these path coefficients. See the path coefficient significance. You can even see this one. See, earlier independent variable 1 had a significant relationship with dependent variable. Now it has changed. It is insignificant. Independent variable 1 is better in predicting this variable, which is acting like a mediating variable to dependent variable. Right? In this condition, you can go to this path coefficient. See the path coefficient. These are the path coefficients. These are the path coefficient. These are the t statistics. These are the p value. Three of the values are insignificant: 0.834, 0.340, and 0.805. How this t is computed? T can be computed by dividing this path coefficient by standard deviation. If you will divide this by this, the standard deviation, you'll get this t statistics. And this should be more than 1.96. That means you need to see this also and this also. Then only you can say that there is a positive or negative relationship between the hypothesized constructs and the relationship is significant or insignificant. Fine. Any further question?
Ma'am, I
Hope you
would like to
understood.
ask the question. Ma'am, my question is related to VIF value. The
Yes.
VIF value which we have calculated in the example we have taken, in most of the
Mhm.
cases, it is coming out to be more than 5. So the very
Mhm.
high values we have removed, but still the values were more than 5. So what treatment should we do in that case? Means most of the values
See,
were near to 6. So,
okay. See, we can do the correction the time you are doing measurement modeling. You can check the cross loading also. From there also the corrections can be made.
okay,
But what we actually think of that if you have to correct the VIF, either you try removing those items, but if you if for suppose you feel that you are dropping more number of items, in that condition probably you are missing on your constructs. So in that condition I will suggest that you increase the sample size, right?
okay,
You
ma'am.
increase the
Okay,
sample size, probably it will help you to mitigate this VIF issue.
okay,
Yeah.
ma'am. Thank you.
But without removing this multicollinearity, you cannot go ahead in predicting your model further.
Okay.
Ma'am, there is a one question in the
Yeah.
chat box.
Yes,
Uh,
please.
How to create k-fold sample from the full dataset?
K4 sample,
K-fold
yes,
sample from the full dataset.
full data set. How you will be making this K-fold sample from the full data set. Although
Yes.
PLS makes it automatically, right? You need not make that, right? See, as I stated before also, assume that you are having 100 students in a class. Remove a small portion that we call the holdout sample, 20%. Remaining are the training samples. That means the 80 students that remain with you will help you in building the model. So first, what you will be doing, you will be, Smart PLS will use the marks of these 80 students to learn the pattern, right? 80 students understood out of 100, हमने 80 students को रख लिया to predict the model. Now, what you will do with the 20 students? You hid 20 students. You have actually left out. You have not used them in modeling the this running the model. So what we will be doing? This 20 students. See, if you see this part, one second, I'm taking you to the PLS predict. These are the folds. Fold 1, fold 2, fold 3, fold 4. You can consider fold 5, right? What I did, I've hold out 20 students over here. Remaining 60, I've run the sample. On remaining 60 or on remaining 80, I have run the model. Again, in the next model, next fold, what I will be doing, I'll be holding out different 20 set of students and I will be running the model because we are doing it bootstrapping, right? This PLS SEM actually takes the help of bootstrapping. That means multiple times this will be done many a times. K-fold cross validation. Third fold, in the third fold, I will be holding out the third set of students. Fourth step, I will be holding out the fourth set of students. Fifth step, I will be holding out the fifth set of students. Right? Right? So for suppose round one, in round one, I have hold uh, student 1 to 20. In round two, I hold 20 to 40, 21 to 40. Three, I hold 31 to 40, right? And so on. So this is like testing the students with many different new question papers to check the consistency, right? Now, how close were the predicted marks to the real marks? Real marks was what? The training sample that you have run on 80. That was your real value, right? And predicted marks is what? The holdout that you have actually computed later. If your predicted value is closer to the real value, that means your model can do a good prediction with the new data set. This was a new data set. This was a new data set that I actually kept aside, right? This was the new data set. And if you feel that your real value that you received by running this training sample is far away, then this new predicted value, that means it's a bad prediction model. That means the predictive relevance of your existing model is less, right? So this is how it has been done. So if predicted value, what you have received by running this holdout 1, holdout 2, holdout 3, 4, 5, 6, up to 10, these are the K folds, right? Is near to this training model. That means it is a good prediction model. If this is this value, this prediction value is far off than this training real value, that means it is a bad predictive model. The predictive relevance of your model uh, reduces. That's what you can say. It's having it does explains, but it's not having the capacity to predict the newer data. Right? That's what we understand. I think I'm clear.
Yes, we got the response in the chat box. Now it's clear. Thank you.
Right?
Okay. Any
Yes,
any
please.
other question? Any other questions from the participants? Maybe there is no further question from the participants.
Okay.
So, thank you all the participants for the today's sessions. And Dr. Chanda Gulati beautifully explained the key aspects of the structural modeling, path analysis, including how to assess the collinearity, so interpret the path coefficients, beta value, t value, p value, and these are the very, very important. And ma'am have very beautifully explained that how we report these relationship in the research paper also. And we also covered the important model evaluation indicators such as the R square for the explanatory powers, F square for the effect size, Q square for the predictive relevance, and the use of bootstrapping for the reliable estimates. So thank you, Dr. Chanda ma'am, for your insightful sessions, and thanks to all the
Thank
participants
you, sir.
for
Thank you
your
so much.
engagement. And we formally conclude day third sessions, and we look forward for seeing you in the next sessions. Thank you so much.
Thank you very much. Let me have, on behalf of the Modern Kashmir Economic Association, a formal vote of thanks also. Before we will go for vote of thanks, I will be sharing, certificate for our resource person and moderator on screen. Let me try it. It is my first, effort. Let me see how it will go. So all participants, meanwhile, you are, advised to open your camera for group photo later. My screen is visible to you.
Yes, sir.
Yes,
So anything is coming or not?
2 files are coming.
So files are coming. So I have to open them, right?
Yes.
Something is happening or not?
Not yet. We are waiting.
Okay, just give me. It is asking. I have to share again. Let me first stop sharing. The file should be there. Let me share now. Are you able to see the screen now?
Now it's visible.
But I am myself unable to check what is going on. So it is visible. Now, dear
Yes.
participants, put your hands together for our resource person, Dr. Chanda Gulati, for enlightening us in today's session, which was based on, it was actually our third day, it was based on structural model assessment and path analysis. We learn about relationship between latent variables, hypothesis testing, PSLM, SAM predictor, and CPPAT reporting. So, on behalf of J&K Economic Association, I would like to extend our sincere vote of thanks to our resource person, moderator, and all participants, and especially organizers, different organizers who have, added this valuable contribution to day three. So, it was insightful to learn about structural equation model, path analysis, discussions which I have already, discussed about that we were discussing about latent variables, model path, and it has greatly enriched our understanding that uh, understanding advanced research techniques we can say. So the way great dedication by our resource person and made the great engagement to make this event very successful. So undoubtedly it will inspire us for further academic and professional growth. We look forward to continued collaboration and learning opportunities in future. Thank you again for your commitment and involvement. So now let us, share our next certificate to our moderator, Dr. Sharif. Is it visible?
Yes, sir. It's
So this was all for day third. It was a great learning. Thank you very much. So now let us take a joint group photo. All participants kindly on your camera if you are able. Let me stop sharing. Yes, participants are there. Thank you. But you are not, good participant because you are not subscribing channel. Neither you are, following our pages on YouTube, LinkedIn, and Facebook. So I hope you will now, try to follow us because all the lectures, whatever you are learning here, they are available for your, lifetime learning. If you skip during the online session, you can sit with, throughout your life, learn from our YouTube. So that is only possible if you are, following and you have subscribed to the channel. So photo session is, done. If you are having questions to for resource person, you can reach her on LinkedIn. You can search. And if you are having questions for organizers, you can reach us. So now we are, as we have taken, a lot of time, more than half an hour more. So we are now closing the session. Thank you very much all. Let
Thank you, Dr. Firdosh and the team for this opportunity. I'm sharing a link of one paper that you may look at, which is actually stating in detail that how you can calculate and report the results in PLS-SCM, right? I've shared this in chat box.
Okay, I will be copying it
So
for
all of you can
participants.
refer to that, right? You please share this with the participants.
Yes, okay, you have shared this citation.
Yeah,
It is freely available.
yeah, it is freely available.
Yes. Dear participants, I have shared it on WhatsApp group. You can just put it in the Google and you will get this paper. So thank you
Thank
very much. Have a good evening to all. Let us, conclude this session. Thank you.
thank you, Dr. Firdaus. Thank you, Dr. Sharif. Thank you so much.
Thank you so much, ma'am. Thank you so